Howdy Bike 410 students. So in the last video, we talked about the first of 4 reversible inhibitor classes, competitive inhibition. And competitive inhibition is the only one of the 4 that you can actually outcompete the inhibitor by increasing the substrate concentration. That's why it's called competitive inhibition. You can compete with the inhibitor because the inhibitor is binding the active site. The other 3 types of reversible inhibitors do not bind the enzyme active site. Okay, so we're no longer going to be binding to the site that the substrate binds. So the first of those is pure non-competitive inhibition. Pure non-competitive inhibition has very classic Michaelis-Menten kinetics in the absence of the inhibitor compared to in the presence of the inhibitor. So we're looking at a Michaelis-Menten plot converted by double reciprocal manipulation into the Lineweaver-Burke plot. And these lines intersect the x and the y-axis in ways that are very informative as to what kind of reversible inhibitor we have. So in this case, where we have a non-competitive inhibition, we know right away that this is not a competitive inhibitor. And that's because Vmax has changed. Remember, Vmax is represented by the y-intercept, the intersection of the line of the plot of your kinetics, which are the magenta lines, intersecting with the y-axis, 1 over velocity. So Vmax is changing. Vmax changing means it's not competitive inhibition. But look what doesn't change. The x-intercept is the same. So that means that the Km is the same. And remember from the first slide for part 2, the inhibitors section, the reversible inhibitors that change Vmax without changing Km are those of the pure non-competitive class. Okay, so what might be happening? And really, we have to draw cartoons to understand these other types of inhibitors. We just know they're not binding the active site. So the cartoon that's provided is shown here, where the enzyme is the gray, strange-looking molecule with different shapes, spaces on it. And the substrate is the yellow thing that's binding to its active site right here. Okay, so this is the active site. And the active site is left open when the enzyme inhibitor binds someplace else. Okay, so the active site is not the site of inhibition. So the inhibitor is this orange box, and the inhibitor is binding either to the free enzyme or to the enzyme bound to its substrate. After all, it doesn't compete with the substrate for the active site. It binds to another site, right? And so this inhibitor doesn't change the binding of the enzyme to its substrate. And remember, your Michaelis constant, capital K sub m, is a approximation of your dissociation constant. And so if your enzyme is binding and dissociating with the same affinity, then your Michaelis constant, Km, is not going to be changing. Okay, so that's why Km isn't changing, because your enzyme inhibitor is not interfering with the ability of the enzyme to bind its substrate. Okay, and the cartoon came after the kinetics. So the kinetics are the data. The data were the initial velocities were measured by the graduate students sitting in the lab looking at increase in intensity as a function of time, and then measuring those initial velocity slopes, and then getting the value of those slopes and plotting them in a Lineweaver-Burke plot, and that's where we got these lines. Okay, so the Lineweaver-Burke plot of non-competitive inhibition is characterized by no change in Km, but a decrease in Vmax. Notice that in the presence of the inhibitor, 1 over V is increased, which means 1 over Vmax. This is 1 over Vmax, the intercept. 1 over Vmax, an increase in 1 over Vmax is a decrease in Vmax, right? If you increase the if you decrease the denominator, you increase the value of 1 over the denominator. Okay, so a decrease in Vmax with no change in Km tells us that this reversible inhibitor is pure non-competitive. Now, keep in mind, if you forgot to dialyze the night before, you got this plot, you would have to consider that this could be an irreversible inhibitor, because it turns out that irreversible inhibitors give the same plot, but the inhibitor can't be removed by dialysis. So you would have done the hard work first if you didn't do the dialysis the night before. Okay. All right. The second type of non-competitive inhibition is called mixed non-competitive inhibition. And mixed non-competitive inhibition differs from pure non-competitive inhibition in that the Km does change. Okay, so in this case, there is interference in the ability of the enzyme to bind to its normal substrate, but the inhibitor is still binding the enzyme at a different place than the substrate. So Lineweaver-Burke plots of mixed non-competitive inhibition can look like either one of these plots. The lines intersect, but they can intersect above the x-axis, as shown on the left plot, or they can intersect with each other below the x-axis. The point is both the Vmax, which is represented by the y-intercept, and the Km, which is represented by the x-intercept, are changing. And so this is a change in Vmax and Km with intersecting lines, because the slope is changing, is the hallmark of mixed non-competitive inhibition. It decreases both Km and Vmax, but the lines still intersect. So what's going on with mixed non-competitive inhibition? We don't know exactly, but there have been some models put out there. The only way to really know is to have a crystal structure, right? So what models fit the kinetic data? And this is one of them, and you don't need to memorize this, but what you're looking at here at the top is your normal enzyme substrate reaction, right? And what happens in mixed inhibition is the ability for the inhibitor to inactivate the enzyme before it binds the substrate or after it binds the substrate. Okay, so that's shown in cartoon form over here, where the enzyme can be inhibited over here without the substrate or with the substrate. Okay, so that is what makes mixed non-competitive inhibition different from pure non-competitive inhibition, is the fact that the substrate binding is actually interfered with, and that's why they put the inhibitor not at the substrate binding site, but near the substrate binding site, because it affects Km and Vmax. Uncompetitive inhibition is different from the other three forms of reversible inhibition in that the slopes of the lines are parallel. Okay, so this is really where you diagnose whether your reversible inhibitor is uncompetitive or not. You never see parallel slopes like this unless you have uncompetitive inhibition. So what's going on in uncompetitive inhibition is like mixed non-competitive inhibition. You have a change in both the x and y intercept, right? So the Vmax is changing and the Km is changing, but the difference is that the Km over Vmax is the same. Okay, so Km over Vmax is constant, which means that the slopes are constant, which means that the lines are parallel. Okay, so we can tell what kind of inhibitor you have, not because the crystal structures look like these cartoons, right? We don't really know the mechanism. We can just speculate what the mechanism is based on the kinetic data. Okay, so what might be explaining uncompetitive inhibition? This is the one that's the hardest to wrap my brain around, so I can imagine this would be hard for anyone. What's going on here is your substrate is bound to the enzyme in the enzyme substrate complex, and then the inhibitor binds. And the inhibitor binding interferes with the enzyme substrate complex. And so the enzyme now binds to its substrate differently. And that somehow affects the Km and Vmax in ways that are compensatory. So you basically shift both of them upwards on the line. So you have a lower Vmax and a higher Km. Here's another example of uncompetitive inhibition. And one of the hallmarks of uncompetitive inhibition is it's only observed in enzymes that have two or more substrates. Okay, so that's not really shown in this cartoon, but what is shown is another way of representing the cartoon in the last slide, which is the enzyme substrate complex is the target of the inhibitor, and it interferes with the way that the enzyme binds to its substrate. Okay, so two hallmarks of uncompetitive inhibition, and this is in red, so this could come up in one of those multiple choice questions. Number one, there are three. Number one, both the Km and the Vmax are changing. Number two, Km over Vmax is not changing, so they have the same slopes and a Lineweaver-Burke plot of their kinetics. And number three, it's only observed in enzymes having two or more substrates. All right, so that ends our three types of non-competitive or uncompetitive inhibition, and our one competitive inhibition, and our irreversible inhibitor. The irreversible inhibitor we can distinguish by dialysis. Competitive inhibition we were able to distinguish by, let's go back to that first slide. We were able to distinguish by being able to reach Vmax at higher substrate concentrations. Oops, slipped right past it. Okay. There's our irreversible inhibitor, which we're going to not be able to dialyze away. Competitive inhibition raises Km with no change in Vmax. Non-competitive inhibition, pure non-competitive, I should say. Pure non-competitive inhibition decreases Vmax with no change in Km. Mixed non-competitive alters both, and so does uncompetitive, but Km over Vmax is the same, which means the lines have the same slope. Make sure you can distinguish between different types of inhibitors based on the Lineweaver-Burke plots.